In this video, we'll discuss an introduction to the elements and history of programming languages. So language, in the general sense, is a mechanism for expressing human ideas. Now, as programmers specifically, we create algorithms to express the process of finding solutions to problems. And then we create programs to express those algorithms to a computer, all of which is done with some form of language. So consider, for example, the problem of finding prime numbers. So the problem specification is some inputs, things like the known rules about primes in the real world, and an input about maybe how many primes we want as a result. And then the output would be a list of that many prime numbers. So notice the problem doesn't tell us anything about the process for finding the solution, just the criteria for evaluating it. Did I get a list of numbers? Are all those numbers prime? Then I know that the answer was correct. Now, a process for solving this problem, that is an algorithm, might look like the prime number sieve. So the idea behind the prime number sieve is we start at the number 2 and we count up one integer at a time, keeping track of all the prime numbers that we find. So for any number that's divisible by one of the primes that we've already found, that's not considered prime. It's called composite. All of the other numbers are considered prime, and we store those in our result. So note that an algorithm is an expression of this process. So I just expressed it here in English, but it could be expressed in a programming language, right? A program essentially computes a process that's expressed in some programming language. So for example, we could see the prime number sieve in Python would look something like this. So we start at 2 until we've reached the correct number of primes. We check each number to determine if it's divisible. If not, then we'll keep it. If so, we'll throw it out, and we just count up one at a time until we've found enough numbers. We could do that, or we could also see the same program in a scheme language. So it's the exact same thing, perhaps a little bit less easy to read, but the important thing here is that the process is independent of the program in which it's expressed, right? The program describes a process. We've seen now 3 different ways of describing this process. So the choice of language is going to control the efficiency and perhaps the effectiveness of communication of that expression. So for example, expressing prime numbers in English or possibly in Python are both quite easy to do, but for a course full of people who haven't yet learned anything about the Scheme programming language, communicating that same process in Scheme may not be as effective from one human to the next. Now, various different languages will have various different advantages and disadvantages, but all languages will consist of the same 3 elements. That is, symbols, syntax, and semantics. Where symbols are the building blocks of a language, syntax is the rules for combining those symbols, and then the semantics is the meaning that we ascribe onto those combinations of symbols. So learning a language often means mastering just these rules, but being a great programmer is about more than just understanding the rules of the language, let's say the symbols, the syntax, and the semantics. In a similar way that understanding chess is about more than understanding how each piece moves. It's about understanding the consequences of those moves, recognizing patterns, and developing strategies. So similarly in language, we must understand why and where expressive complexity arises in our language and how to manage it. So to understand the emergence of complexity in languages, it will help to observe a brief historical context. So modern high-level languages are built on top of their predecessors. We build complex programs that are dependent on complex compilers and interpreters that are themselves complex programs dependent on other complex compilers and interpreters. This causes layers of abstraction that hides the complexity of all of it, but it also hides the motivations for those lower-level developments. That is to say, we can make programs without ever understanding how programs even work. This makes for a powerful approach to development, but it also creates a bit of a shaky foundation as well, where we may not understand the consequences of the underlying design choices that led us to what we now consider normal. So, a historical context to illuminate some of those developments. Now, the history of programming languages can be started pretty much as far back as you'd like. We could go to the Jacquard looms and player pianos of old, and possibly even the designs that influenced those. But let's jump ahead to the first electronic computers, circa 1940 or so. So the first electronic computers were massive machines. They filled rooms and consumed copious amounts of electricity, and they had very little computational power to show for it, at least relative to today's standards. So programs for these machines were written in what's known as machine language. sort of binary encoded words that requested hardware instructions in order to act on data. So it's essentially hardware implemented instruction sets. So there were machine instructions to add, compare, load, unload registers, and do all sorts of other basic tasks, but they were quite tedious to program any sort of high-level computation, much like, for example, constructing primes. But one of the design choices, or one of the design influences, I should say, for this era was that computers' time was considered to be more valuable than the programmer's time. The computers were very expensive machines, so there were very few of them. So there were teams of people would line up in order to essentially book time on these machines. There's a special mention worth pointing out in this same era. There's a language called Plankalkül that was created by Konrad Zuse, a German mathematician, between 1941 and 1945 or so. And this was a typed, relatively high-level language that was structured and followed an imperative design choices. It had features like assignment, conditionals, arrays, loops, records or structures, and even exception handling. There's even a chess-playing program written by Zuse in this language, but the entire thing remained theoretical and unpublished for many years due to other historical events around the time. So programming, unfortunately, would remain a machine-language interaction for many years to follow. But around the turn of the next decade, so in the 1950s, or 1949, let's say, assembly languages started to emerge. And these were a notation that abstracted the binary interaction into a more human-friendly format. So it abbreviated names for machine instructions and gave labels for registers and flags, which made it so that a human could read this without having to interpret it as well, or a well-educated human at least could. So originally, these assembly languages were one-to-one mnemonic translations between assembly and machine language, so one assembly instruction corresponded to one machine language instruction, but ultimately macro expansion allowed for single commands to abstract larger complex operations. Now, it's worth pointing out that the assembler was required to translate from this assembly language into machine language, which is to say, we couldn't just write programs for the machines anymore. We were now writing programs that had to be translated into something the machine could understand. It's still a bit tedious to program in assembly language, but at least programmers could be different from the people who built the machines. So, as an example, here's the same problem for solving the list of the first n prime numbers, but in an assembly language. So as you can see, it's a bit opaque to understand. You could work your way through it and try to figure out the different parts. The comments definitely help. This is also a modern assembly language, so it has a bit more power than what the assembly languages would have had when they first emerged 70 years ago. But there's a bigger problem than just the opaqueness. People could learn this language and be able to express in it, but one major issue with assembly code is that it was still machine dependent, much like machine instructions themselves, which means if we wanted to program for a different machine, we needed to construct an entirely new assembly language as well. This leads us to the compiled languages that arose through the 1950s and 60s. So compiled languages are essentially high-level machine-independent languages. They decoupled programs from the processor instructions that they were evoking. Okay, so they abstracted away all of the details of the underlying machine and let us focus on the problem in the domain itself. Now, in order to make this whole system work, a compiler was required to translate from the high level down into the individual machine codes. So compilers were still specific to a given machine, but they could handle the same language over various different machines. Okay, so they'd essentially take one language and translate it down to the specific machine instructions for whichever machine they were installed on. Now, a bunch of languages of the era that might be familiar to you. Fortran emerged in 1957, which was the first language to implement a compiler. Lisp emerged in 1958, which was the originator of the entire functional programming paradigm, which had a bunch of useful features like garbage collection and such, which were novel for the day. Algol emerged around the same time as well, which is the ancestor of all modern imperative programming languages like Java and C. And COBOL also showed up, which is an interesting language because it was written with the specific design intent of having a human-friendly syntax. So it signified a move from the machine domain towards the human programmer in the design of languages. So following this development of compiled languages, since there were so many languages and some started to emerge, through the late 70s and 1980s, there was actually an explosion in programming languages, all arising out of those first few languages from the previous era. So in the 70s, we saw languages like C and Scheme from this course and Prolog, Pascal, Smalltalk, and SQL. In the 80s, we saw languages like C++ and Ada, Common Lisp, Objective-C, MATLAB, many of these languages still in common use today. Now, in this era, the focus moved towards the human side of this human-computer interaction, where the emphasis in the language design was on readability, maintenance, and scalability. We wanted the human to be able to look at code, understand the code, and be able to comprehend it so that they could develop more robust programs. Features like modularized code, structured data types, commenting conventions, and descriptive variable names, these all took popularity during this era. Now, a feature that fell out of popularity in this era is what's known as the goto. So gotos were replaced by structured constructs here. So the goto statements were effectively too powerful for general usage. So a goto statement is so powerful that it's considered a bad idea to use them. The problem being is when you see a goto, you can't tell if it's being used to simulate a loop or a branch or a function or who knows what else it could be doing. Instead, they were replaced by structured constructs like if, for, while, case statements, and that sort of thing. Throughout this era as well, compiler technology improved. So originally, when the first compilers arose in the previous era, humans could make better programs than compilers still. If a human sat down and went through and translated one of the high-level languages down to a machine code, they would do a better job than these automated compilers could do. But as machines got more complex, so too did the compilers. And soon, automated compilers were creating better code than their human counterparts. What this means was that there could be a design shift in the hardware itself of these computers, where the hardware could be designed for compilers rather than for humans. All right, and moving into we call the modern era, although it's quite a large gap now. From the 1990s onward to today, the emphasis has continued in a consistent direction, moving towards simplifying programmer effort. So Moore's law says that roughly every 2 years, the number of transistors that could fit onto a chip has doubled, all while costs steadily decline. So throughout this era and through the eras that precede it, electronics become smaller and faster and cheaper, essentially at an exponential rate. What this means is the programmer labor becomes far more valuable than computational time. So the general goal now is to simplify the design and maintenance to essentially reduce the amount of time a human has to spend considering these problems, or equivalently to improve the expressiveness that a human can convey. So a bunch of user-friendly language features became quite common, things like garbage collection, having fancy IDEs or rapid prototyping toolkits, all that facilitate large amounts of construction with minimal human requirement. One of the major paradigms that emerged in this modern era is object-oriented programming. The popularity more or less took the forefront in most programming languages. It's a simpler or a more natural programming design, which is structured in a way that's similar to how we consider things in the real world. So the movement in the language was toward the domain level, while still remaining general purpose enough to solve the wide array of problems that we can solve. One of the main features in object-oriented programming is an emphasis on reusable components. So once we construct this object, we can do so in a general way or using generics that we can simplify how that same component can be reused in a number of other domains or a number of other problems as well. So languages like Java and Python and Delphi became quite popular in this era. Java in particular had a large following throughout the 90s, though it's falling out of favor nowadays and being replaced by other modern object-oriented languages. Also in this era was the development of the internet. So the internet provided new avenues for language development. For example, JavaScript became the language of the internet because it was included early on in Netscape Navigator, became the de facto language for doing all sorts of fancy things on the client side. And PHP for web server deployment was also a language that was developed out of a necessity to meet this new challenge. Also found in the languages of this era was an emphasis on concurrent programming. So this is due in part to the notable increase in multiprocessor machines. So most phones nowadays have at least 4 cores, but also due to the creation of GPU programming APIs. So these both allow for very high throughput of processing if we can structure our expressions in a parallel way. That is to say, if we can divide our problem into a number of sub-problems that can be solved concurrently, then we can take those sub-solutions, combine them into the ultimate solution for the original problem. So this emphasis on concurrent programming also influenced the resurgence of functional language features in modern languages. So pure functional languages don't have side effects, so concurrent processes don't need to worry about any sort of shared mutable data or race conditions. This makes functional design solutions very appealing in concurrent implementations. Also, the popularity of JavaScript, which was influenced by Scheme, a functional language, pushed the adoption of a number of functional language features into most modern languages, whether they started with them or not. So features like lambdas and first-class functions and tail call optimization, these are either being included in the design of new languages or added into the revisions of old ones. So looking forward, it's difficult to make predictions about what will come next, but we can already see that Moore's law is approaching its physical limit. Effectively, the transistors are now so small that they can only fit a single lane of electrons through, which means if they get any smaller, they'll become unreliable. So the machines of old will have to give way to the machines of new. To that end, quantum computing is on the horizon. It's actually at the edge of commercial viability right now. And this is a type of computing that's designed for orders of magnitude faster computation, using concepts of superposition and quantum entanglement in order to produce computation. Now, the language for such computers will likely draw from this historical context, but it will certainly reveal new challenges, motivations, and aspects of design as well. So it's clear that no language was developed in a bubble. So here's an incomplete map of a language genealogy. You can click on this link to get a closer view of the picture. It only goes down to 2003, so many languages are not included in this, but it gives you a pretty good sense of the fact that no languages were created out of thin air. They all have their motivations. Any of the languages that you've likely programmed in, like C or C++, Java somewhere else over here, these all have their influences that drove them. Okay, so yesterday's language features get borrowed and mutated to become tomorrow's big new thing. So the study of novel paradigms will inform a broad understanding of this language spectrum as a whole. So that's it for this video. In the next video, we'll talk about the fact that there's so many languages now that we can actually study different categories of languages, known as programming paradigms.